Hi everyone, I'm going to present you an efficient HTN to strips encoding for concurrent plans. So this is a translation from an HTN problem to a strips problem, which aim at producing concurrent plans. So let us first define these two ways of planning. First, we will start with the strips planning way of defining a problem. We define an initial state and a goal state, and we say that the problem is solved whenever we find a sequence of action that will result in the goal state when applied to the initial state. So in strips planning, we represent a state as a collection of propositions. The propositions are the property that are verified by the object within the problem. And in the same way, an action is a combination of two sets of propositions. The first set of propositions represent the precondition set, which are the propositions that must be verified in order to apply an action, and the effects set, which are the propositions that will be modified when applying the action. And so finding a solution plan means finding the sequence of action that will result in a goal state. So we start from an initial state here, and we try to find the sequence of action that will result in a goal state here. In this case, the solution plan would be the sequence A1, A2, A3, and so on. Now, a concurrent plan is a plan where instead of finding one action between the states, we find what we call a layer of actions. This is a collection of actions which are all mutually independent, meaning that their effect does not interfere with each other. For the HTN planning, an HTN planning defines a goal as a task network. This is a collection of tasks that must be performed in order to solve the problem. These tasks are ordered by an ordering relationship, explaining the order in which the task must be planned. So for instance, you have an example of a task network here. We have 4 tasks here, and the edges of the graph represent the ordering constraint. So for instance, the T1 task must be planned before the T2 task. The tasks in a task network can be of 2 types. The first type are primitive tasks, which correspond to an atomic task of the problem. It represents to applying an action within the solution plan. And a compound task is a task that can be decomposed into other tasks. So it can be either a primitive task or compound task. This way of decomposing a compound task is described by a method, which is also a part of the problem. So for instance, as a convention, we usually denote the primitive task with lower cases and the compound task with upper cases. So in this task network, we have 3 primitive tasks and 1 compound task. And the decomposition of this compound task is described by a method. Let's say that we have a method decomposing T3 into 2 primitive tasks, T5 and T6, and we obtain the resulting task network here by decomposing the T3 task. And finding a solution plan of the HTN task network means finding a solution plan that resolves a task network decomposed from the initial task network. So for instance here, this task network has been decomposed from the initial one, and this plan is a resolution of the task network above. So this is a solution to the HTN problem. Now let us talk about our motivation about translating an HTN problem to a strips problem. So first of all, an HTN problem is more explainable more expressive than the strips planning, and it also fits way better into the human way of planning, and offer plans that are more explainable for a human being. However, the vast majority of researchers focus on search and heuristics of strips planning and does not focus very much on HTN planning. So translating an HTN planning to a strips planning is a way to alleviate these discrepancies. In that regard, our contribution is twofold. We first proposed an HTN algorithm which produces concurrent plan that we call CPFD, and then we encode this procedure as a strips problem, which can be solved by any strips planner. So let us discuss about our algorithm, CPFD. So this algorithm starts from a task network and try to build a concurrent solution plan based on this task network by, at each iteration, selecting a task that is not constrained and resolving it. So for instance, here we have an initial task T0, which is the only one that can be selected. So we select this task and we apply a resolution of this task. So in this case, this task is a compound task. It can be decomposed using a method. And let's say we have a method decomposing into 4 tasks, here 3 primitive and 1 compound. So at the next iteration, we select a task that is unconstrained. Here, there are 2 tasks that are unconstrained, T1 and T3. We can pick either, but let's say that we pick T1. Since T1 is a primitive task, resolving T1 means adding the action corresponding to T1 to the solution plan. So we check if it's possible to add T1 to the first layer. If it is, the action is added to the layer and the task within the task network is marked as buffered. It means that the task is not yet removed from the task network, but it cannot be selected anymore. So at the next iteration now, we select another task that is unconstrained. So T1 is still unconstrained, but it cannot be selected again. So T3 is the last task remaining. We select this task, and since it is primitive, we do the same. So if it can be added to the layer, the first layer, it is added here. And we go to the next iteration. But at the next iteration, no task is available. So we apply what we call a layer switch, which means applying the effect of the task contained in the first layer, obtaining a second state S1, and then the process iterate from there, but with the state S1 instead of the initial state as the current state. So the algorithm stops whenever there is no more task left in the task network. All right, so that will be it for this presentation. If you want to see the actual HTN to strips encoding of the algorithm I just presented, please refer to our paper or come to see us at the workshops. Thanks.